solving the equation of motion. So yeah. So let's do an example for understanding it better. So let's suppose we have a function equals f of x equals to x minus 5. And we need to find a solution to f of x equals to 0. So anyone here easily can solve it by just adding 5 to both the sides. So we have x minus 5 plus 5 equals to 5. So that means x equals to 5. So this is the analytical solution. This is the analytical approach to the problem because just we know that we had to add 5 and we find that x equals to 5. But the numerical solution differs so much by that. So for the numerical solution, let's guess x equals to 2. So we calculate f of 2, which comes out minus t, which is a negative number. So then we calculate for another value of x, that is x equals to 6. So f of 6 equals to 6 minus 5 equals to 1, which is a positive number. So we now know that the answer must be between 2 and 6 because x minus 5 is a continuous function. So the root, that is x, where x equals to 0, must be between 2 and 6. So what we do is calculate the average of these two numbers, that is x equals to 6 and x equal to 2. That comes out to be 4. Then use x equals to 4 in calculating the value of the function once again. And it comes out to be minus 1, which is again a negative number. So we once again know that it must be between 4 and 6. And this is how all the calculators and be it in your computers or your phones or just your scientific calculators, calculate the solution to these equations. This is called a bisection method, and this is the numerical solution. So yeah, we will be simulating the two-word problem later in the presentation. So let's talk about the numerical methods in detail, as numerical methods play a crucial role in simulation across various fields of science and like including physics, astronomy, fluid dynamics, and more. So what we'll be doing is solving the differential equations required for the two-body problem using numerical methods. So we have this equation, that is the derivative of velocity with respect to time is equal to the second derivative of the position vector with respect to time equals to acceleration. And we know that the acceleration of a body in the two-body problem is equal to g times the mass of the other body upon x square, where x is the distance between those two bodies. So basically, by like the most easiest approaches, we calculate the dv, that is for calculating velocity, we just cross multiply the term dt. So we have dv equals to a times dt. So dv can be written as delta v, and delta v equals to a times delta t. So we have the new velocity. So basically what we do in numerical methods is we calculate the new, like overall we run a for loop. So in for loop, we keep calculating the new velocity, and using new velocity, we calculate new position of the object, and using the new position, we calculate the acceleration. So we keep doing it for like thousands of steps. So v for v new will be equals to v naught plus acceleration times delta t. And it's an important point to note that acceleration equals to dv upon dt at v equals to v naught. Sorry for like I might have mistakenly wrote it, but it is acceleration equals to derivative of velocity with respect to time at v equals to v naught. So we keep doing that for thousands of iterations to calculate the new position and velocity of the object for simulating the two-body problem. This method is also known as the Euler method, named after its discoverer. And so one more point I would like to add is this delta t is known as the step size. So like it's pretty accurate. Like that's how we literally solve these equations.
Sanidhya,
We
hello.
Yeah.
The screen came now.
Oh,
It
okay.
was. It just came.
I don't know what the problem is, but it's fine, I guess. It's done. Yeah. So like this model is like pretty accurate, and this is how we actually calculate DV. So for new position minus initial position, we actually just integrate this. So what in terms of integral, we actually follow this method. So we so this method is pretty accurate in a sense like it does follow what calculus taught us, but actually there is a slight problem with it, that we know that like what should be the step size. So ideally calculating while in calculus, we know that dt tends to 0. That is the step size which we are using here is tends to 0. So that is delta t equals to 0.00 times like like many times, so many times 0 and then 1, which is like we clearly cannot use this value of this step size, as it will literally take hundreds of thousands of iterations just to simulate the bodies for even 1 second. And we need to deal with simulations that take hundred of million of years. So clearly, we cannot use this ideal value, that is dt tends to 0. Theoretically, we can calculate like we do using calculus, and Newton had his form, like Newton made some formulas on calculus, which helps us in doing that. But computationally, like if we try to simulate this, it's not feasible by any chance. So one more method, like one more approach you might say is let's take the value of delta t to be like smaller, but not that small. Let's suppose that we take the step size as delta t equals to 0.001. So there is no problem in that, but actually what happens is with some functions, let's say, yeah, this function. So what happens is if you take the value of delta t equals to 0.001, which is a small value, but as with if compared to the value of dt, which should be tending to 0, it's like clearly the larger value, like clearly much large. So what happens is if we just go back in this equation, we know that v nu equals to v naught plus a times delta t, where a is the tangent at v equals to v naught. So this is the tangent at y equals to y naught. In that case, v equals to v naught. So if we take delta t equals to 0.001, so we are actually multiplying the acceleration by this value. So what we have now, that is y1, that is v nu, is this y1. And if our function is this, like the varying like this, then what happens is it creates an error. And you can actually see that it's a pretty significant error. And let's say our function is a continuously decreasing or continuously increasing function. So what happens is this error keeps adding up. And what it results in is like orbits like this. So if we computationally calculate computationally try to solve the two-body problem using numerical methods, using the Euler method in specific. So what happens is the trajectories and the orbits would look like this, and it's a total mess. So yeah, that is why we cannot take delta t equals to 0.001 as the error adds up. And also, if we take such small values too, it will take 10,000 iterations to simulate just 10 seconds. And as earlier I talked about it, we have to simulate for like millions of years. So it's not feasible. So what we actually do is we use another numerical method. So this numerical method, which I will be using today in simulating the two-body problem, is called the Runge-Kutta method, also known as the RK4 method. So basically, these are the algorithms. So yn plus 1 is actually vn plus 1, and tn plus 1 equals to tn plus h is, so tn plus 1 minus tn equals to h is the step size here. So basically what this method does is calculate the weighted average of slopes at different points in this equation. So let's see here. So now if we compare it to Euler method, you can see that the error is significantly less. So yeah, so I won't like dive into the explanation of this method, but for now, it's like, for now, you just need to keep that in mind that the error here is significantly less than the error present in the Euler method. Also, in the Euler method, the error is directly proportional to delta t, whereas in the RK4 method, the error is directly proportional to the delta t to the power of 4. So that's why we will be using the RK4 method. So I just wrote some points why we should use RK4. So RK4 requires fewer steps to achieve the same level of accuracy, reducing computational load for given precision. So in Euler case, if we require 10,000 iterations to simulate the orbit, for RK4, as we can use delta t values much larger, we can have that same result in like 500 iterations. Also, RK4 is stable regarding like, it is stable and can deal with many of the differential equations. And as I talked about it, it involves intermediate calculations. So by evaluating the slope at multiple points within the time step, RK4 provides a more accurate approximation of the solution. So it is calculating the slope 4 times in this time step, that is from T0 to T1, that is the time step between them is delta T. So it's calculating the slope 4 times, which results in more accurate results. So yeah, clearly clearly we can see why RK4 is superior than Euler method. So now let's try simulating the two-body problem. So for simulation, I will be using Blender. So what Blender is? Blender is a powerful open source 3D creation software which can create a wide variety of content, including animations, visual effects, 3D models, simulations. So we will be using Blender because it also supports Python. So using Python or any other coding language as such, you can simulate physically, real world physical simulations. And yeah, so Blender offers robust physics engines and simulation tools that allows user to create realistic animation based on physics laws. So yeah, I'll just share the Blender screen. 1 second. Uh, is my screen visible now?
Oh, yes, the screen is visible.
Yeah. So this is the Blender interface. So we have this Python terminal integrated in the Blender software. So basically, this is the whole code. It So basically, if I tell you the gist about simulating, so it involves three things. That is defining various functions. Like for simulating the two-body problem, all we require is just one acceleration function, that is gm upon x square. And Second thing, you need to specify the initial conditions, and which we did already. And the third is the follow. So we are for this program, we will be using 500 iterations to calculate the position of these objects. So I'll just show you the simulation. Yeah. So this is the 1 kg object, 1 unit mass object, and 2 unit mass object. So like few things that you can notice is its center of mass is fixed, and both of these orbits, both of these follow elliptical orbits, and one of the focus of these two elliptical orbits is their center of mass, which if the initial position of object 1 was 12 and the object 2 was -6, if we calculate the position of the center of mass, it will come out to be the origin. So they are revolving in elliptical orbits around the center of mass, which is the origin. And so the line joining these two objects will always pass to the origin. Also, if you can clearly see as they are far, their velocity is less, and as they come close, their velocity increases. That is in accordance with the Kepler's laws. That is, the aerial velocity always remains constant. So yeah, this was the simulation part. So basically, the point of this presentation was to introduce to you the numerical methods and how these numerical methods are used in simulations. As later on in this presentation, we will be talking about the three body problem and the n body problem. And you will know later that these numerical methods are the only solutions to these two problems. So let's just dive into the three body problem. One second, I'll just share the presentation once again. Is the presentation visible?
Yes, yes.
Yeah, okay. So let's talk about the three body problem. So unlike the two body problem, the three body problem has no general closed form solution. That is, the three body problem does not involve any, like you cannot express the position of those three objects using just mathematical expressions. This is because of when three bodies orbit each other, the resulting dynamical system is chaotic for most initial conditions. And the only way to predict the motions of the bodies is to calculate them using numerical methods, like which I discussed earlier, that there is no analytical solution present to the three body problem, only we can solve it using the numerical methods. So before talking about chaotic systems, let's talk about the history of the three body problem. So Newton in his book also talked about the three body problem. But actually, Newton was unable to resolve the three body problem. He just had talked about his approach to solving the two body problem. So what Newton theorized was, let's see this. So in this GIF, you can see that Earth and Jupiter are revolving around the sun. So as Earth closes towards the Jupiter, because Jupiter is such a big planet, its gravitational pull is also like very high. So whenever these two planets close down to each other, the gravitational pull will tug the Earth around it. So what Newton thought was, for so many years, if whenever Earth will come closer to the Jupiter, its gravitational pull will kind of, let's say, will interact with its will just change the trajectory of the Earth. So if these gravitational pull sums up, it might result in Earth being pulled out of and thrown away out of the solar system. So yeah, before so this is the three body problem is very, very similar to the two body problem, but it's much harder to attack just because there is no analytical solution. So after Newton, there are certain special cases of orbit that were discovered by Euler and Lagrange. And there, so these solutions usually had some special property of symmetry, or in which one of the bodies could be considered of negligible mass. That is, so these solutions, so these solutions have there was these solutions have been summed up in the in our module, and we have talked about the Lagrange's points, the five Lagrange's points. So on those points, three of them were Euler points that Euler discovered the special case of symmetry in which these three planets were collinear, and Lagrange later on discovered the other two points, that is L4 and L5. So I have this video which will help you better in understanding all these 5 points. Yeah.
A rotating coordinate system. This rotates.
I hope it's audible
Anand,
now.
I think the screen is stuck again.
Uh,
Now it's back. Now it's back.
Assume we have an
is it
object.
audible now? Hello?
Yeah, it is. It is.
That orbits
Yeah,
the
okay.
sun along with the Earth. We're going to use a rotating coordinate system. This rotates at the same speed as the Earth moves. So, in this coordinate system, the Earth doesn't move. Now, let's look at all the forces that are at work here. To account for the fact that this coordinate system is rotating, we have to add in a centrifugal force that pushes out away from the sun. Then we add in the gravitational force of the sun and the gravitational force of the Earth. This graph shows us the effective potential energy, and it tells us how objects will move. An object whose orbit starts here will slowly drift towards the sun. An object starting here will slowly drift towards the Earth. And an object starting here will slowly drift away into the outer solar system. But an object won't move if the surface is flat. The surface is flat at 5 points, called the Lagrange points. The first 3 points were discovered by Euler. The remaining 2 were discovered by Lagrange. The last 2 Lagrange points are stable. This means that if an object is slightly off from the point, its orbit will shift slightly, but not too much. The first 3 points are unstable. This means that if an object is just slightly off from the point, it will just move further and further.
So yeah, that were the 5 special points, the 5 special solutions to the three-body problem, which were discovered using symmetry. So let's now talk about chaos theory. So if I tell you, like, if we delve into the history of this, so in 1888, King Oscar of Sweden and Norway put forward a prize. So the problem was to come up with a particular sort of solution to the three-body problem. So actually, as there is no solution to the three-body problem, no one was able to meet the conditions as written. But Henry Poincare won the prize because of his paper, which in which he actually proved how the three-body problem is almost impossible to solve. So what he introduced, so Henry Poincare showed that the three-body problem exhibits sensitive dependence on initial conditions, which is a hallmark of chaotic systems. So what are chaotic systems? So chaotic systems are those systems the in which the position, like the final position of all these simulations and everything, exhibits a sensitive dependence on the initial conditions. If you just change the initial conditions, like by, let's say, 1%, let's just say 0.1%, the final outcome could be totally different. So this is what make the system chaotic. The three-body problem is a classic example of a chaotic system. While the specific solution exists for particular initial conditions and configurations, just we saw about those 5 points, but no general closed form solution has been ever found. So uh, this is an animation about three bodies which were actually close placed very closely, like their initial conditions varied like by 0.1%. And as you can see, as time goes on, their trajectories just trajectories just change a lot. Like they just follow new trajectories and just don't follow each other now. Like earlier they follow each other, but finally they just followed really different trajectories. So this is the butterfly system. This is a butterfly effect in place. That is the final outcome varies, like the final outcome is completely different from the initial conditions. So now let's talk about the n-body problem. So the n-body problem is similar in this way to the three-body problem, that is does not have any closed form of solution or analytical solutions. We have to once again resort to the numerical solutions for just finding positions of the n bodies. So here's a really good video, or kind of just an introduction to the n-body problem.
In 2009, two researchers ran a simple experiment. They took everything we know about our solar system and calculated where every planet would be up to 5 billion years in the future. To do so, they ran over 2,000 numerical simulations with the same exact initial conditions, except for one difference: the distance between Mercury and the Sun, modified by less than a millimeter from one simulation to the next. Shockingly, in about 1% of their simulations, Mercury's orbit changed so drastically that it could plunge into the Sun or collide with Venus. Worse yet, in one simulation, it destabilized the entire inner solar system. This was no error. The astonishing variety in results reveals the truth that our solar system may be much less stable than it seems. Astrophysicists refer to this astonishing property of gravitational systems as the n-body problem.
So yeah, that was the n-body problem, and that was the exact reason why Newton was actually so worried about the three-body problem, that what if the orbit of Earth goes unstable in near future. But for now, at least for now, we know that for the next 100 or million of years, the solar system will remain stable, and the orbit of all the planets will remain as they are and not go unstable. So yeah, that was my part of the presentation. So now Vishwajit will present. So I'll just share his slides. Are the slides visible?
Yeah.
Yeah, one
Uh,
sec. Yeah, one sec. Yeah.
Hello. So, yeah, as Sanidhya mentioned before, uh, when satellites are launched from the Earth, we take into consideration other orbits and where exactly we want to send the satellite to. So, let's say we want to send a satellite or a rocket from Earth to Mars. Now, here we want to send a satellite with the least possible fuel consumption because we can only take so much amount of fuel into space without it being wasted. So, rather than time, fuel here is our number one priority. So, we can calculate what fuel exactly does is it gives an impulse. So, what we want to actually calculate is the least amount of impulse you can apply for the satellite to actually go and meet the place where it's supposed to be. So how exactly we do this is something called as Hohmann transfer orbits. So first we put our satellite in a low Earth orbit, that is the number one, the first orbit, which is circular, and then at the point where the 1 and 2 meet is when we give our first thrust, and it puts the satellite in the second orbit. Now this orbit is elliptical and it touches both 1 and 3. The place where we want to reach is usually at 3. So we at Earth we calculate what is the right time such that uh, we can go to 1, 2, and 3. And at the time when the satellite goes from 2 to 3 is when the planet where we want to go to is at 3. So this is called as Hohmann transfer orbit, and it has been proved that this is the least cost efficient. This is the most cost efficient way to go from orbit 1 to orbit 3. So this is not just Earth and Mars. This can be used for transfer or orbits from any co-orbiting massive bodies. Next. Now, there's also another thing that we use to optimize the fuel consumption, and this is called as slingshotting of satellites. This how exactly this works is we have two satellites which are sent for very long range missions. In the sense, we wanted to go out of the solar system, and we also want to go it fast so that we actually see the satellites images, and it's not the next generation which sees it. So how exactly we do this is we use the power of the other planets that are there in our orbit. So as you can see, Voyager 1 used Jupiter, Saturn to slingshot it. How exactly slingshotting works is uh, we know that uh, because of conservation of energy, in the frame of reference of the planet, the speed of the object which is coming and going will remain the same at the endpoints. But this is only in the frame of the planet. So we know that the planet is moving. So if we can time our satellite right, then we can give it a boost in the direction of the movement of the planet. Because in the uh, planet's frame of view, we want to be moving at the same velocity. Now, Voyager 2 used even more planets, that is Jupiter, Saturn, Uranus, and Neptune, and this helped it go even faster with while we are using the same amount of fuel. Next slide. So here you can see it being actually used. So at A part, we can see that the the blue satellite is actually slowing down because it went in the opposite direction of the planet. and E is the ideal scenario, or in the planet's frame of reference, where you can see the speed actually does not change. And F is ideally what we want to happen, since we can see it go even faster than what it was going at. G is what we don't want to happen, because we don't want our satellite to come back to us. Next slide. Now let me talk about another gravitational phenomenon called as tides. So we all know that there is the sun, which is a very big source of gravity. This actually, because the gravitational force is dependent on distance, different points at Earth actually show different values of gravitational pull. So this actually, because the oceans are fluid, this actually pulls the oceans to form a very small ellipse. This is obviously quite exaggerated, but it forms a mini ellipse. Now, this ellipse depends on two things. Since the moon, although it is not as heavy as the sun, is quite close to the earth, so we have to see two things when we want to see the tides. So that is the sun and the moon. Now, when the sun and the moon are in a straight line, these effects add up because they want to bulge the ellipse in the same direction. So this is called as a spring tide, also known as a high tide, and this causes a very high overflow of tides. Now there's a second case when both of them are perpendicular to each other. This is when their effects cancel out, since one of it wants to bulge the ellipse in the x-axis and the other one wants to bulge the ellipse in the y-axis, but we only have a finite amount of volume. This actually reduces the tide from what it could have been. This is called as a neap tide, and the sun actually is around half the value of the moon. The effect of the sun's gravity is half the value of the moon. So the moon tide uh, kind of overpowers the sun tide. So usually the tides are closer to the moon. And this is also the reason why we have two very high tides every day, because as you can see, the moon wouldn't have moved that much in a day, but the earth would have moved a lot. The earth would have completed a whole rotation, and these peaks would have just passed by whichever part was there. Next. Now, that was for fluids. Now, let's say the sun was actually very close to the earth. Now, then this differential force effect would have also applied to the rocks and the solids in our earth, which would have caused the earth to get broken apart. So, if earth wasn't massive enough, the sun's gravity would have ripped apart the earth if it was close enough. So, this limit, that is the distance at which two objects can be close together and orbiting without it breaking apart the other object, is called as the Roche limit. And this explains the formation of rings of Saturn, which is assumed to be other stellar objects going too close to Saturn without it having its own self-preserving force, which just breaks it apart and forms a ring. Here there's a visualization of how it happens. Can you play the video? So the black mass is a very heavy mass, and the white mass is something that got very close to the heavy mass. You can see that first it becomes an ellipse, and then it starts splitting apart. So you can see how it actually forms a ring. And this also happens when there are two different stars close to each other, and this ring is also called as an accretion disk. Now the image on the left is actually the comet Shoemaker-Levy 9, which got too close to Jupiter and actually got broken apart, and this image was taken of it. Sanidhi. Now let me talk about one of my favorite objects, that is the black hole. Uh, as we have all heard before from somewhere or another, a black hole is a high density region which does not even allow light to escape from it. So these are usually remnants of when stars go end end their lifetimes, and these stars were more than 14 solar masses. So this is predicted by not Newtonian mechanics, but actually general relativity. But we can express the stuff that this does in Newtonian mechanics if we assume the something known as a potential function. A potential function basically takes in input as any point in space and gives out a gravitational potential value. Now we can also treat light as a point particle, and we can run a simulation for the point particle coming into the black hole, and we see that we actually predict from general relativity that it would move just like a point particle. And when we do the calculations in Newtonian mechanics, we can see that it does the same. So since it also warps the path of the light, we can treat black holes as a lens, and this is a test for general relativity. Next. uh, so this is a from the left hand side, a black hole is coming, and we can see how the light is being warped. We can also see that it at some point forms a small ring when the light source is right behind it. This is called as an Einstein ring. Here's a video on.
An Einstein ring is a very cool feature of gravitational lensing where a background galaxy gets stretched out into a full ring around the foreground lens. Molten ring is a really interesting case where it's one of the largest galaxies that forms a near complete Einstein ring. The molten ring, you have a very large cluster of galaxies that has magnified this background galaxy. Einstein's theory of general relativity is really sort of what predicted these Einstein rings in the first place. He created this whole machinery for how gravity is supposed to work. Matter would tell space-time how to curve, and space-time would tell matter how to move. And then as you have light moving through this curved space-time, those equations led to the prediction that this light would almost move on what seems like curved paths and cause the phenomenon of gravitational lensing, which is where this light gets essentially bent and distorted by a foreground lens, like a galaxy cluster, and creates these stretched out images that are magnified of these distant galaxies that we see. It's definitely a bit of an optical illusion, so if you were to take the gravitational lens completely away, then these background galaxies would just look like, you know, the normal everyday galaxies that we see at these distances. And it'd be a lot harder to pick apart what's going on in their inner workings. So the gravitational lensing effect, it is kind of like looking, you know, at a funhouse mirror. It makes the background object appear a little bit bigger, a little bit distorted. You know, just like you go to a funhouse and you see, your head looks gigantic, your body looks tiny. It's a similar effect, but we can use it for science as opposed to just, looking at ourselves and saying, oh, wow, that's kind of funny. The Hubble Space Telescope has definitely taken the clearest images of the Einstein rings, and they've really, verified this part of Einstein's theories of general relativity. They've really, shown us a lot more about how gravitational lensing works, and really sort of pushed the limits of what we can learn about these distant galaxies with gravitational lensing.
So yeah, a little bit more on the gravitational lensing Einstein ring part. So as you can see, this the radius of this ring actually depends on the distance from the black hole and the size of the black hole, and we can actually calculate it given the uh, function, the potential function, and we have done that in the module, so you can check that out in the module. So yeah, that is it from me. Check out the module; it has a bit more information and the calculations on what I have told. Yeah, any questions? Well, if there aren't any questions, then you can feel free to like just send a message in the group or the teams, and we can clarify it later.
So we'll keep the meeting on for 2 to 3 minutes. So if anyone has any questions, they can just text it in the chat, or you can just unmute yourself. So it seems like there are no questions. So thank you everyone for joining us today. And if any questions arise later on, then you can post it on the Doubts channel or on the WhatsApp group as well. And as already mentioned, these sessions are just for introduction. They're just to get your interest. But please do go through the modules. It is not a substitute. So thank you everyone. If you guys do not have any question, then you are free to leave.